Here we are. I promised fuel injection, and you're going to get fuel injection. So we're going to take a look at this in two different stages. So there's two main fuel injection systems that we're going to see. We have the RSA or bendix fuel injection system, then we have the Continental fuel injection system, which works similar, but there's some fundamental differences. Now, the reason that we're covering fuel injection now at the end of float carburetors and pressure carburetors is because we're kind of following an evolution in technology. So what you're going to see with the fuel injection system is very similar to what you've seen with our fuel delivery methods prior to this. Now, the biggest difference here is we're going to use similar concepts as a pressure carburetor. But remember, one of the things that we did with a pressure carburetor to eliminate things like icing is we moved the actual fuel injection point past the throttle plate. So on a pressure carburetor, our fuel injection or our injection point would be past the throttle plate. That way we don't have that significant temperature reduction in the venturi over here, which ends up resulting in icing conditions. We're going to take that one step further with fuel injection by moving our injection point all the way out to the inlet ports for the cylinders, which is going to further help prevent things like icing and is also going to help produce a better distribution of fuel across all cylinders, which tends to help us with things like single cylinders overheating due to uneven fuel distribution. So we get some solutions from fuel injection as well. So this is a simplified diagram we're starting off with. So we're going to start with our RSA bendix system. And let's talk a little bit about how this works. Let's talk about the familiar. So first things first, something you should recognize is right here, this diaphragm system that we see similar to the pressure carburetor. And we're doing the same fundamental thing. We're going to have our air metering force between the A and B chambers, and then we're going to have our fuel metering force between our C and D chambers with their unmetered and metered fuel pressure. Now, the way that this works is fundamentally the same. Our differential in air pressure in the A and B chamber is going to move a valve which allows fuel to flow out to the injectors. Pretty straightforward. So let's talk about how these systems work. So first off, we have our impact or ram air, which is coming in from the throat of or coming in from the entrance to the fuel metering device, or in this case, our throttle body. We don't really call it a carburetor because it's not a carburetor, it's a throttle body. So we have ram air pressure, which is coming in through impact tubes that are mounted at the entrance to the throttle body, and it pressurizes this chamber. We also have our venturi pressure, so we're taking that low pressure or suction pressure from the venturi and we're sending it out to this chamber over here. Now the way that this works is at idle, we have a special spring which is installed on top of the diaphragm over here, which is in our venturi pressure chamber. And what that does at idle is it keeps this ball valve just off enough to provide idle fuel flowing out to the injectors. However, as we start to accelerate, right, we're going to have a higher pressure for our impact tubes, and we're going to further reduce the pressure in our venturi, and that's going to have the tendency to force our diaphragm to move this way, like so, which is going to further unseat the servo valve. Now on the other side, we have two forces that are acting on this side of the diaphragm that can help balance things out. So on one side, we have our unmetered fuel pressure, which is coming in past our mixture control. And basically we can think of that as our fuel pump pressure, which is filling this chamber. And then, boy, we'll need a different color here. We have our metered fuel pressure, which is going to come in past the metering point. So what's actually being allowed to be delivered out to the fuel injectors, and they'll fill this one. So as we have a lower metering pressure, that means we're going to have a lower amount of fuel flowing through. We're going to have a lower area of fuel pressure over here, which is going to counteract some of the motion that moves that servo valve out. So if we have higher pressure with our unmetered versus our metered fuel pressure, it's actually going to act against our air metering force. However, as we start to increase the amount of fuel flow, we're never going to have a situation really where our unmetered fuel pressure is higher, or rather that our metered fuel pressure is higher than our unmetered fuel pressure. But as they start to equalize, then we don't have an opposing force that's working against our air metering force, and so we allow the air metering force to more or less decide where that servo valve goes. pretty straightforward. Up here, the things we'll recognize from the cockpit is we have our mixture control, which is part of our fuel control unit. So it incorporates a fuel strainer that goes into the unit. And then we have a linkage to our mixture lever. And with the RSA system, we also have a linkage that goes to our throttle lever. So in this case, the mixture control right here, that's the red lever in the cockpit. That's what controls our actual rich to lean. And then we have this idle valve, which is linked to our throttle control. So the position of this air valve, you can see the dotted line right here, is actually mechanically linked to the idle valve. And we'll talk a little bit more about how that works in a second. So let's take a look at this fuel, the servo regulator right here, and our fuel control after that. So looking at our servo regulator, this is a more detailed drawing of what we were looking at up at the top. So here we have our diaphragm that separates the two air chambers. So on this side, we have our, I know it's in there. We have our venturi pressure, sorry. We have our venturi pressure. And then on this side of it, we have our impact air. And then on this side, we have our fuel diaphragm right here. So we have the unmetered fuel pressure on that side of the diaphragm and metered fuel pressure on that side of the diaphragm. Now what we're looking at in this drawing right here is the condition of the system at idle. And so we'll notice a couple things. We have this diaphragm is completely bottomed out against the regulator body. So basically it's at its closed position, or as close to closed as it's going to get. But what I want to draw your attention to is this constant head spring right here. And you'll notice that there's actually threads and a nut. What that means is that's the adjustment for what our idle fuel flow is. It's important to note that when we're at this bottomed out position, we actually do have a slight path for fuel to flow from our metered section out to the flow divider or out to our fuel injectors. So we actually have a small passage that allows for that, and that is effectively our idle setting for fuel that's moving through this portion of the metering system. On the other hand, what we notice on the right side is what happens when we're outside of the idle circuit. So as we start to increase our throttle, we have a decrease in pressure on this side of the diaphragm and an increase of impact pressure on this side, which compresses our head spring over here. And this constant effort spring actually helps to unseat the diaphragm. When that diaphragm unseats, it pulls this entire assembly out of this valve body. And what it does is it creates a larger opening for fuel to flow out to the injectors. Pretty straightforward, and it works very, very similar to what we see with a pressure carburetor minus the poppet valves. Now as we take a look at our mixture section, this is a little bit different. So this is an expansion of what we looked at before. So up here we have our fuel inlet. So we're going to have fuel flowing in from an external engine-driven pump right into there. The next part of this is we flow through a fuel strainer. This fuel strainer is serviceable by a technician. Things like that adjustment for our idle setting in the air metering section, all that, that's not adjustable by a mechanic. That's going to be done in an overhaul facility. But we can do things like service a screen, which comes out right through this fitting on the outside. So we'd remove the fuel inlet fitting, and then we would remove this entire body and it pulls straight out. Now with this system, we come from our filtered section and it goes down into our metering section. Now on this side, we have the lever which is connected to our mixture control. On this side, we have the mechanical linkage that is hooked up to our throttle valve, which is then in turn hooked up to the throttle control inside the cockpit. And the way that this works is we have our metering jet right here, and we have a variable slider. You'll see a couple different versions. It may be a slider similar to what we see in a float carburetor. It could be two discs on top of each other. Whatever it is, we're restricting passage from this section to flow through. So the way that you look at these two is this lever right here, controlling mixture, is going to determine the maximum amount of fuel that can flow through the fuel injector and be regulated down to whatever the fuel injectors need for that power setting. This idle lever valve connected to the throttle is really just there to take the entire system out of idle. So with a pressure carburetor, you saw we had a couple different things with like an idle metering spring and diaphragm that allowed the idle system to automatically come out of idle when we started to reach certain engine speeds. This does it a little bit differently. We just have a mechanical linkage that physically turns this portion of the body and is going to effectively cover up the idle passage and open up the main metering jet for fuel to flow through. This rotating portion right here is going to restrict how much fuel can flow to get to that metering jet, if that makes sense. We have kind of a two-part here. This one is not really directly controlled by the pilot other than the fact that they move the throttle back and forth, but this one is. It allows us to choose all the way from full rich to lean all the way back to idle cutoff to shut off the engine. As we flow through, we have this unmetered fuel pressure, which is being taken off to be measured in the servo regulator. And then we have our metered fuel pressure. It's past our metering point. It's going to be sent out to the servo regulator as well to be able to pass out to the fuel injectors. So that's what we're looking at there. As we come back out a little bit, we can take a look at our system here. So we've covered what happens up in the fuel control. Right, this is that mixture control lever we talked about. It controls the amount of fuel that flows to the main metering jet. And this idle valve is going to rotate as we reach basically anything off idle to open up that main metering jet. And then we have the unmetered fuel pressure that comes over here, and we have our metered fuel pressure that goes here. It gets ready to send out to the injector. So relatively straightforward. Now let's talk a little bit about things happening downstream. Let's talk about what's happening past the servo valve into our flow divider and our actual fuel injecting nozzles. And just as an aside, in case you want to see what this looks like from the outside, here we have the fuel inlet. This is our mixture control body right here. And this is that mechanical linkage that I'm talking about. And this actually gives us two things. So we have our idle speed adjustment. So it's similar to what we'd see on a float carburetor with a screw that basically controls our idle stop. And then we have our idle mixture adjustment, which is actually the linkage that connects the throttle plate to that idle valve we're talking about. And depending on how long or short this linkage is, it's going to control how much of that idle valve is either covered or uncovered when we're at idle speed, so it changes our idle mixture. Pretty straightforward. Over here we have our metered fuel outlet. So that is what's going out to our flow divider and our fuel injectors. Which, speaking of the flow divider, let's take a look at this real briefly. So our flow divider, as you can see here, we have fuel that's coming from our regulator. So this is out through the servo valve and is coming into our flow divider. And there's two pieces right here because this needs to be able to operate at idle. It also needs to be able to operate at a higher engine speed. And the difference is when we're in our idle circuit, all of the control for the maximum amount of fuel that can pass through is coming from the fuel control itself. As we start to get into higher speeds and higher pressures, especially like full throttle operation, we have specific fuel injectors that allow a certain amount of fuel to be sprayed into the engine. It's matched to the engine and the fuel injector servo type. And so once we get into that high power range, we have our metering jet, which is going to regulate from the servo, but then ultimately these nozzles are going to be the de facto endpoint for how much fuel can be scheduled into the cylinders at any given time. And so we really want to separate those two circuits. So the way that this works, you'll notice that we have a bleed right here that goes to the top and hits a diaphragm. And the way that this works is when we are in our idle circuit, we do not build up enough pressure to unseat this entire body that opens up the passage to allow us to flow straight out to the injectors. We take this bypass, which in turn unseats a poppet valve and allows fuel to leach into those sections. Pretty straightforward. However, once we build up enough pressure, then we're going to be able to force up against this metering spring right here. It pushes the diaphragm up, and then we open up the entire passage so we have straight fuel flow from the regulator right out to the fuel injectors. This right here is going to be exposed to atmospheric pressure. If we happen to be operating with a turbocharged engine, then we would have a manifold that lets it read upper deck pressure so that we can schedule fuel appropriately, and this diaphragm will act with the right pressure, very similar to what you see with a compensating fuel pump that allows it to read upper deck pressure to know how we can change our fuel flow rate depending on altitude and power setting. The other piece we have right here is a small bleed port that goes to our flow meter. Now this is going to be based upon pressure, but based on the pressure that it reads, it's going to indicate flow through the injector servo in gallons per hour, typically gallons per hour. One note about this is when we're troubleshooting, because this reads pressure rather than actual fuel flow, if there is a clog or a restriction in the system, then it could mess up what our fuel flow is, because again, it's not actually reading the total quantity of fuel flowing through. It's reading how much pressure that we get from the system and then turning that into a number for an approximate GPH for the pilot to be able to understand up in the cockpit. So a couple different things about that can be challenging, but ultimately it makes sure that the pilot knows what's going on, but it's not an absolute reading. Last thing we're going to talk about with the RSA system are our injectors. Now, over here at the injectors, as we look at a diagram of these, they're going to look very similar to primer inlets, but the biggest difference we'll see is that we have a shroud right here which covers a screen air over bleed holes. Now, the whole point of these bleed holes, so we look over here, we have air that's able to come up into the injector and mix with fuel as it exits through the nozzle. And what that does is it allows the fuel to atomize more evenly and more effectively so that we get actual burnable fuel air mix. If we didn't have that air bleed, then we'd just shoot a solid stream of liquid fuel into the port and it wouldn't burn very well. So that doesn't help us out a whole lot. So you'll see two versions of this. You'll see one for a naturally aspirated engine that's not going to operate at very high altitudes. And we just have a shroud with a screen over the bleed holes that act as a filter and that allows it to draw in air. If we have one that is going to be at higher altitudes, we'll see this additional line that connects it to upper deck pressure or to the turbocharger section. So you'll see two lines that come into this fuel injector. We have the fuel line, which comes into the top, and then an air pressure line that comes into the side and allows the fuel injector to maintain that high air pressure even when we're at high altitude because it uses discharge from the turbocharger. That's the RSA system. Hopefully that makes some sense. Now we'll take a look at the Continental system and see how this differs from the RSA system. So again, we're going to start off with a simplified drawing for our Continental system, our TCM system. And one thing you'll notice is that this is going to be a little bit different in the way it's constructed. This incorporates a constant output pump. So we have a vane type pump that's a part of the injector. We refer to it as the injector pump. But we're going to have some similar points as well. We have our fuel air control unit, which is going to use air pressures to determine how much fuel should be scheduled. We have control via a mixture level, and we have lever, and we have control via a throttle fuel lever, which is attached to our throttle air valve. And then we have a manifold valve, which is similar to a flow divider, but it's a bit different specifically for the Continental system. So we'll take a look at that as well. First things first, though, I want to talk about how this system operates. Now, one thing you notice with the RSA system is that we have constant pressure going into the fuel servo. In this case, our fuel servo, or our injector pump, is providing its own pressure, which means it has to have relief paths in order to make sure that we don't overpressure the system. If we overpressure the system, then we schedule too much fuel. What this does, however, is it allows us to choose how much fuel is going to flow out to the system. So we have a mixture control lever here with a valve that opens and closes a relief path that goes back to our pump. We have a couple relief paths. We have a bypass right here that can go past the injector pump if we lose drive to the injector pump. But as fuel flows out of the injector pump, it goes through a strainer and goes to our fuel air control unit. Depending on the possession of the mixture control, it's going to control how much fuel is relieved back from that outlet pump. Then we have our main metering jet right here, which is going to control the maximum rate flow that can go through the system, and our throttle fuel valve, which is linked to our throttle air valve that acts as a final gate that allows fuel to flow out to the manifold valve. So we don't have the same situation going on with different diaphragms and everything like we'd see with a pressure carburetor or the RSA system. This is kind of a different animal altogether. And we're going to take a look first at some of the intricacies of this injector pump. So let's pop down here and take a look. There's two states that we're looking at with this injector pump. One is a naturally aspirated engine, one is a turbocharged engine. So I'm going to show you quickly how the fuel flow operates through this system. So under normal operation, we have fuel inlet, which is coming from the tank. This could be provided a number of different ways. We could have a boost pump coming to the system. It could be potentially gravity fed, but usually not. So we're going to see a boost pump filling this or priming this pump. Now we have our collecting chamber right here, and there's a couple of relief valves. Number one, we have a bypass valve that allows fuel to flow past this pump if the pump is not working properly. But otherwise, if everything's working correctly, this pump rotates and we supply pressure to this other side. Now we have a couple different features that can be incorporated. We have a pressure outlet for measuring unmetered fuel pressure, and then we have the outlet to our fuel control. Now, we have two settings on this system that are going to result in different states of operation. We have our low unmetered fuel pressure, which is typically going to be in action on our idle circuit, and we have our high unmetered fuel pressure, which is going to be supplying the engine at higher power settings. So the way this works is we have fuel that can flow out to the injectors, which is going to be regulated by that mixture control lever and the throttle control lever. Any excess fuel is going to flow back through two different pathways. We have excess fuel that flows back to the tank through the vapor return and is going to flow through this vapor separator venturi. And the idea of that is the fuel flowing through the venturi is going to produce an area of low pressure. As vapor collects at the top of this housing, it sucks the vapor out and sends it back to the fuel tank, so we have a good solid supply of fuel going to the injector. This other pathway that we have is ultimately our adjustment for how much fuel pressure is going to be supplied. Now, the way this works is we have our first stop, which is our high pressure adjustable orifice. Now, the thing is, this is only really going to come into effect when we're at very high power settings. This pump is going to be turning very quickly. We're producing high pressure, and this orifice is going to act as a restriction, which sets the baseline of high pressure that we can have. However, when we're operating at lower pump outputs, this really isn't going to have that much of an impact. And so what we're seeing act as our actual bypass is this relief valve for unmetered low pressure fuel. So we have an external adjustment for that as well, and we can change basically our low fuel pressure setting. Now, once we start to accelerate past idle, this relief valve is going to remain open, and then this adjustable orifice does most of the metering for us. In a turbocharged engine, the only real big difference that we have is instead of having a static adjustment for this metering orifice, it's attached to an aneroid, which is attached to our turbocharger discharge. So it's reading the upper deck pressure. As upper deck pressure feeds in, it's going to vary the width of this orifice, and it's going to change our high pressure setting. Relatively straightforward. So we've covered this section, our injector pump. We know that we are sending a certain amount of pressurized fuel depending on the power setting of the engine. Now let's take a look a little bit further at our mixture control. So with our mixture control, we can see both sections. We have the mixture lever, and then we have our throttle lever. Now the way this works, if we're in full rich, we have fuel that's coming from that injector pump like we just saw. It goes through a strainer, and then we have a variable valve which is going to allow fuel to flow out to the main metering jet, and then the throttle valve. This throttle valve is going to restrict how much fuel can flow through. And remember, as we create a restrictor point up here, we're going to have that injector pump relieve fuel the way that it was doing before. We just control the amount of demand. So rather than having a metering point that opens when we have the right pressures, we actually have supplied pressure constantly, and then depending on our demands for the position of the controls, it'll allow a certain amount of fuel to flow through, and the rest is just returned either to the front of the pump or back to the tank. So we have a return line in both cases. So up here at full rich, we have absolutely no fuel that's being allowed to go back to the pump inlet. It's all being scheduled out to the main metering jet and the throttle valve. We can also see right here, this little enrichment valve is open at that point at full throttle. Now, as we're in the lean position, our stop rotates, so we're sending some of the fuel out to our main metering jet, but we're also sending some of the fuel back to our pump inlet, which is changing the overall amount of fuel that can go to our fuel valve and out to the manifold valve, our flow divider, and our injectors. Then when we hit our idle cutoff position, we completely block off the fuel path that goes out to the flow divider, so we effectively cut off fuel from the engine. And that's the way it works. And what makes this clever is, since we have a bypass to the injector pump and we have a bypass to this system, if we run, say, the boost pump with the mixture in full cutoff, it actually allows us to purge any vapor in the lines pretty effectively, so we don't have to worry about fuel vapor getting stuck and causing an issue with starting when the engine is hot. It helps us clear out vapor lock and problems like that. As we take a look at the differences with our flow divider, like I said, it's similar, but it's a different design because it has different demands. We have our fuel inlet that comes in through the top, and we have a screen here that protects the injectors and the fuel divider. As fuel starts to come in, right, we'll flow in through here and we'll flow up through the screen. We can offset this diaphragm just enough to allow fuel to flow in and upset this poppet valve right here, which allows a small amount of fuel to flow through, down, and out to the nozzles. Pretty straightforward. That covers our idle setting and allows us to flow some fuel out. Once we build up enough pressure in this section, we've compressed this poppet valve, we build up more pressure in this section, and it actually starts to force this entire body upward against the spring tension, which again is vented to the atmosphere or to our upper deck pressure, and it moves this whole body up, then opening the pathways to our injectors fully to full fuel pressure coming through in full flow. Again, it can be a little bit complex, but this is the most advanced thing that we have running for reciprocating engines at this point. And frankly, it works pretty well. It does a good job. That's a very, very brief crash course into the differences between the RSA and Continental fuel injection systems. We'll talk more about this in lab as we tackle your lab projects, but hopefully this made things a little bit more clear. Now that we've covered all this, the next stop is going to be looking at turbine engine fuel control systems, which is just even a little bit more complex, but hopefully it'll make some sense as well. Thanks for watching. We'll catch you on the next video.